Salah is one of the hottest places on Earth, with temperatures often reaching 50 degrees Celsius. But here in the heart of the Algerian desert, a project is underway that could help to mitigate the problem of global warming.
We are at the very beginning of a whole new program of dealing with fuels and energy that is responsive to a relatively newly recognized problem of climate change. And Salah fits in because it is developing the technologies and the experience for putting carbon dioxide underground.
In order to reduce greenhouse gas emissions at a time of increasing global energy demand, there is growing recognition of the role that underground storage of carbon dioxide, or CO2, could play, particularly in relation to electricity production. A range of techniques are available to capture the CO2 in the first place. Using pre-combustion capture, hydrocarbon fuels such as coal and natural gas can be converted into hydrogen and CO2 through a process known as reforming. The hydrogen can be used in power stations to produce electricity, whilst the CO2 can be injected into secure geological formations, typically 2 to 3 kilometers underground. The main byproduct of hydrogen combustion is water, so this offers the possibility of cost-effective near-zero emissions electricity generation. The two main options for storing the CO2 are depleted oil and gas fields and deep saltwater-bearing rock formations. These are composed of permeable rock such as sandstone, with pore spaces that absorb fluids like oil, gas, water and CO2. When topped by impermeable cap rock such as shale, these fluids are permanently trapped underground. But if CO2 storage is to be widespread, we need to demonstrate its integrity and to test and develop the techniques required. And this is where Salah fits in. At Salah, CO2 is mixed with natural gas in a reservoir being developed by BP, Sonatrach and Statoil. Some 1 million tons of CO2 per year has to be removed from the gas before it can be sold. In the past, this may simply have been vented to the atmosphere, but at Salah, a $100 million project has been set up to compress and re-inject it nearly 2 kilometers underground back into the reservoir, where it should be securely stored for thousands of years.
C'est notre responsabilité vis-à-vis au respect de l'environnement, de notre planète, des générations futures. L'autre bénéfice que je peux mentionner aussi, c'est l'expérience que l'Algérie et les shareholders vont apprendre par cette technique de réinjection et prouver donc au monde que c'est une technique viable, sûre, contrôlable et économiquement rentable, donc pour pouvoir l'utiliser dans le futur dans des cas similaires.
At Salah, the CO2 is being injected into saltwater-bearing rock around the periphery of the area where the gas is trapped. Over time, as the gas is extracted, the CO2 will move back into the main production area. A great deal of work has been done to predict and model the various mechanisms by which the CO2 will be trapped in the reservoir.
We would expect the CO2 to be taken up by the water, so there is an absorption component just in exactly the same way as you get Perrier CO2 within water. There will be some CO2 taken up by the minerals, so we would expect some deposition of carbon on the actual matrix of the rock, and then the residual would actually migrate structurally up dip and into the hydrocarbon trap over time.
The fact that Salah has held natural gas and CO2 under pressure for millions of years provides a high degree of assurance that the re-injected CO2 will remain indefinitely in the reservoir. But it is important to understand the factors that could lead to CO2 seeping out, and to be able to monitor stored CO2 over the long term to ensure that this doesn't happen.
It's very important to demonstrate that carbon dioxide can be stored safely underground, that we understand what's happening to it both in the short, medium and long term, and that we also understand the impacts of carbon dioxide coming to surface should that happen.
The oil industry has many years of history of managing fluids in subsurface geology, and these fluids would be stored several miles under the ground. And there are a number of techniques that can be employed in the oil and gas industry to monitor fluids that could be specifically tailored to monitor the carbon dioxide that would be geologically stored.
At Salah, a monitoring program is being set up as part of a planned joint industrial project involving academic and commercial institutions from around the world. The program will monitor the CO2 over the 20-year life of the field, and a wide range of monitoring techniques are being evaluated. One idea is to establish a permanent seismic array. A vibrosis truck will zigzag across the surface, sending out sound waves that will be picked up by 3 lines of microphones buried in the sand. The resulting seismic images should track the movement of CO2 within the reservoir. Other monitoring systems will measure gravity changes in density between water, gas and CO2, as well as electromagnetic changes that occur over time. Some of these techniques, including seismic and electromagnetic, could also be used at a downhole level, within the wells themselves. And it may be possible for some of the seismic equipment to detect the natural creaks and groans of the reservoir as the CO2 moves through it. Another option being considered is to drill an observation well to monitor the CO2 at one specific location. This could also provide a platform for downhole seismic equipment. At the surface, changes in soil chemistry that could result from CO2 seepage will be monitored through frequent soil sampling. Another focus is the wells that are drilled both to extract the natural gas and to re-inject the CO2. Cement is used as a seal between the rock and well casing during production, and to seal the wells when they're abandoned. There is a possibility that the wells could provide a route for CO2 to seep out. The cement used will be analysed in order to develop the most effective sealing materials. Taken as a whole, the data collected at Salah should help to demonstrate the integrity of CO2 storage and provide a range of monitoring options that can be used at different storage sites, paving the way for the implementation of similar schemes.
I'm very confident that CO2 storage can be done effectively and safely, and in fact we have the technology today. We know how to drill wells, we know how to operate facilities for injection, we have reservoir simulators that predict the performance both in the short and long term. We have monitoring technologies that today that we know can detect very, very small amounts of CO2 in the subsurface. What we need is we need to convince others that the technology works like we expect it to, and we believe it does. And I also foresee that the technology for geologic storage of CO2 will evolve and improve over time.
So, with successful demonstration at Salah and the appropriate policies and regulatory frameworks in place, CO2 storage could become a major part of our response to climate change.
I think the future for carbon capture and storage is going to be focused on capturing the carbon dioxide at electric power plants that are running on natural gas or coal and putting that carbon dioxide underground. The project at Salah is a warm-up exercise for this much larger program of carbon capture and storage from power plants.